Yesterday we studied about half bridge inverter. We had an introduction of what is inverter, classified our inverters into various types according to the supply, according to the output wave shape, and if it was a thyristor inverter, then we had classified in terms of commutation, and obviously according to the connections in series parallel inverters. And then we briefed into our half bridge inverter, studied with R and RL load, and solved the problem. Okay, so today is full bridge inverter, full bridge VSI, voltage source inverter. So it's almost same as your last class only. Okay, so if you understood your yesterday's lecture, today's lecture will also be very easy for you to understand. Okay. So this is my one voltage source EDC with positive terminal, negative terminal over here. 4 switches are there: S1, S2, S3, S4. 4 diodes: D1, D2, D3, D4, D3, D4. Corresponding to S1, that will be D1. This circuit, if you recall, this is same as your class E chopper. Class E chopper is nothing but your full bridge converter. Only mode of operations are different. Okay. So over here, this will be the direction of current that will be entering. That will be positive. So this is my I naught. Okay, and this is plus minus. This is V naught. Okay. So I naught is entering my load, and because I naught is entering in this direction, this will be my plus minus V naught. This is my standard polarity of the load across the load and standard direction of the load current. Now, how we were studying yesterday's half bridge VSI, we were turning on the switch once, then turning off the switch and drawing our circuit and analyzing it. Same over here. This diodes D1 to D4 will be used if the load is inductive. If the load is resistive, there is no use of this diodes. So these are basically feedback diodes which feedbacks the inductor energy to the source. So first what we'll do, we'll study using R load, do the analysis, do the Fourier analysis, find out the harmonic components of the RMS voltages or currents, whatever is required, and then we'll go on to the problem regarding this, then RL load. So in R load, if you recall yesterday's lecture, there was 2 mode of operation, mode 1 and mode 2. In mode 1 was 0 to pi by 2. If you recall, we had written 0 to t by 2, and mode 2 was pi by 2 to pi. 0 to pi is what was our mode 1. That is 0 less than equal to t less than equal to t by 2, because it is a half cycle. And the next half cycle, that is the negative half cycle, is pi to 2 pi, which is t by 2 to capital T. So that is what we will study now. So mode 1, 0 to t by 2, 0 less than equal to t less than equal to t by 2. Your axis is t taken over here, you have to write t over here. If you take omega t, no problem, you could have used omega t over here, omega t. So this axis would have been that pi, this point would have been 2 pi. Right, you can understand positive cycle of sine wave, negative cycle of sine wave. Okay, you can use this meaning also, this reference also, but when you are using this one, use time t, small t over here, because capital T is time period. That's why we have written like this. If you use omega t, this limit should be in terms of pi, 0 to pi. Okay, please be careful about which limit you are using. No problem of using both the limits. Okay? So first one. So what will happen? In the first case, switch S1 and S2 will be on. So if S1 and S2 is on, current will start flowing from this EDC plus, go through this S1, go through this load in this direction, go through this S2, back to this EDC minus. So the current direction that flows is same as I naught. So obviously we will get a positive current, and the voltage, since the current is entering in this direction, this side will be plus, this side will be minus. So comparing that voltage with this V naught will give you again positive voltage. So that's why we'll get positive voltage and positive current when S1 and S2 is on. So when S1 and S2 is on, this was our S1, this was our S2. Current flows from EDC plus S1 through load S2 back to minus. So current direction this one, and obviously voltage polarity, this side will be plus, this side will be minus. So V01 is having positive voltage, and what is my voltage supply will be equal to EDC. So if we apply KVL, you will get V01 is equal to EDC, and I01 direction is this direction, which is same as I0. Just now we had seen in the main diagram. So I01 is also positive. So I01 is positive, voltage is also positive. And remember, we are studying full bridge VSI, so we are using total voltage as EDC. Previously was a half bridge, so we are using the voltage EDC by 2. 2 EDC by means 2 voltages were there, which were having each of magnitude EDC by 2. Now over here, one total voltage is used, that is EDC. Now we'll draw this V01 as EDC during what? 0 to T by 2. So a load voltage is EDC 0 to T by 2. Up to T by 2 we are getting EDC. What is happening to the current? Since it is a resistive load, there will be no charging and discharging. Current will also be constant. What will be my current? EDC by R. My load voltage is EDC. What is my load? R. So EDC by R will be my load current. Supply current is DC, so it will be constant always. Okay. Supply current is DC, it will be constant always. Now what is the current flowing through S1 and S2? Will flow during this cycle. I can say that I01 is only the current that is flowing through S1 and S2. What is I01? EDC by R. So EDC by R is shown over here. During this period, S1 and S4 are off, so no current will flow through S1 and S4. So IS1 and S4 is 0. Up to this completes our mode 1. Now next, our negative half cycle. Mode 2, T by 2 less than equal to T less than equal to capital T. Or you can write pi less than equal to omega T less than equal to 2 pi. Whichever you take your axis over here. Now, what will be on now? Now, which switches I am giving pulse? S3 and S4. Now, if you give your pulse to S3 and S4, current will start from this positive, go through S3, enter the load in this direction, flow through this load through S4, back to this negative over here. Now current direction changes, so current becomes negative. Now as current is entering in this direction, voltage positive will be this direction. This will be plus, this will be minus. So voltage polarity has also changed. So obviously my voltage will also come out to be negative. Now, if you look into the main diagram, see what I have explained using our main circuit, it looks that same. So it starts from EDC plus, goes through S3, goes through this load, goes through S4, back to EDC minus. Okay, and what is the current direction? I02 is in this direction from right to left. Compare your I01 direction with this one. Okay, means this I01 has been compared with the standard direction and written positive and negative. So I can think I01 also as a standard. So comparing your I02 and I01, both directions are opposite. So I02 is in this direction. So obviously I02 current is negative. Now what will be V02? Because polarity has changed, again compared with V01. See, polarity has changed, so V02 will come out to be minus EDC, that is negative. So during T by 2 to T, we are having a negative voltage and negative current. So what is the magnitude of the negative voltage? EDC, minus EDC. So it is drawn minus EDC during this period. What will be the current? Minus EDC by R. So see, minus EDC by R, the minus sign over here, minus EDC by R. Now during this period, which switches are on? S3 and S4. So obviously S1 and S2 current will be 0. So S1 and S2 current during this period is 0. Now for S1 and S2 current is 0. What will be happening to S3 and S4? The current that is I02 during this period, that is nothing but a load current, which is this one negative. But again, yesterday I told you that switch current can't be negative, so we have to represent this load current in positive direction only. So EDC by R represented in positive direction. Then again 0 and continues. So this is how your full bridge inverter operates when R load is connected. Again, if you compare, there are two modes of operation in R load. One is this half cycle and the another half cycle. That is your negative half cycle. So whenever there is R load, remember there will be two modes of operation. Whenever there will be RL load, there will be four modes of operation, because over there diodes will be used. Here there is no use of the diode. Here all functions are through switches only. So up to this, anybody is having any doubt, you can tell me, or we will continue. So we'll continue with the next one. Which one?
ये लास्ट যে ওয়েভফর্মটা আছে ওটা একবার বলুন তো, এই IS3 IS4 যেটা বললেন।
IS3 IS4 is the current through S3 and S4. So if you see your mode 1, is S3 and S4 connected in the circuit? No. So this current will be 0. IS3 and IS4 লিখতে পাচ্ছি না ভালো করে। IS3 and IS4 will be 0 because no S3 and S4 is connected. But over here S3 and S4 is connected, so obviously a current will flow through S3 and S4. What is that current? This current, load current I02. What is I02? Negative, already drawn over here, negative, right? But in a switch, yesterday only I told, if you take a diode, MOSFET, IGBT, anything, current will flow from anode to cathode only. No opposite direction current is possible. So I0 through IS3 and IS4 should be represented as positive current. That's why this I0, even though it is negative over here, it is represented as positive current over here, because you see your load is a resistive load, is a bilateral element, so current can flow in both directions. But your switch is a unilateral element, so current can flow in only one direction, so only positive current. ঠিক আছে?
Yes.
About circuit equations, calculations same like yesterday. You just recall yesterday's facts and do the calculations. You will find it easily. We'll just go through it very quickly. How to do these formulas directly, I'll tell you very easily. If you understand your previous yesterday's lecture, it will be very easy for you. First of all, it is a symmetrical square wave. I told you for a symmetrical square wave, RMS and average value is equal to its magnitude. So what is the magnitude? EDC. So it will be EDC. So RMS and average value will be the maximum value, that is your EDC, or your magnitude of your symmetrical square wave. So anyhow it has to come EDC. You can do by integration method also. So what is the integration method? See, I have told you, you can use this limits 0 to t by 2 integration 1 by t, or t by 2 is nothing but pi and t is nothing but 2 pi. You can use that limit also. Okay, you can. I have used limits in terms of pi. That's why my different integration is with respect to omega t. If you had integrated with respect to t, then this would have been dt. Okay, please take care of that. Whatever you do the integration, but in a square wave, there is no need to do integration, and a symmetrical square wave, RMS and average is always equal to its maximum value. That is EDC. So E0 RMS is equal to EDC, and E0 average is also equal to EDC. Next one we need to find out is the instantaneous output voltages and the harmonic components. So we had written yesterday a equation, V is equal to Vm sin omega t. Okay, so E is equal to means Em sin omega t. What is this Em? That is your Cn value and sin omega t. Okay, So using Fourier analysis, we will find out Cn, that is root over an square plus bn square, and phi n is equal to tan inverse an by n. Now again the same thing, you are getting a square wave symmetry, so your an will be 0 and bn will be 0 for all even values of n. So an equated as 0 over here, and bn for all even values of n will be 0. Then what you do, integrate it 1 by pi whole cycle 0 to 2 pi. Then what you do, I told you, take 4 common over here, so you will get pi by 2 over here. So 4 multiplied brought inside the integration will give you 2 into 4 by pi by 2 into 4, so that is 2 pi, nothing but this one. So 4 taken outside, 0 to pi by 2. So 0 to pi by 2 means half of this. So half of this magnitude is same EDC. So E naught omega t can be replaced by EDC. So E naught omega t can be replaced by EDC. So that gives out to be 4 EDC by n pi. Now, if you recall yesterday's facts and calculations, what we did, Bn was 2 EDC by n pi. Why we were getting 2 EDC by n pi? Because there was EDC by 2, right? Now, it is twice of that. So, whatever the value we had got in half bridge inverter, over here it will be twice. This is how you remember the formulas. Okay, you can't derive each and every formula every time and find the equation, because you are seeing now only so many formulas are there, so many equations, so many graphs. Power electronics is full of these things. So you have to relate each and every circuit with one another and try to remember the formulas, because all this will be required for solving problems. So previously was 2 EDC by n pi because my voltage was half. Now my voltage is double. So multiply with 2, what you will get? 4 EDC by n pi. So whatever values we were getting, RMS values and all, maybe is the switch ratings and all the values in half bridge converter, half bridge inverter will be multiplied by 2. This is the conclusion. Okay. Then we'll find out Cn. What is that? An square plus bn square. An is 0, so Cn will be equal to Bn. What is Bn? 4 EDC by n pi for all odd values of n. Phi n will be tan inverse an by Bn. So An is 0, so tan inverse 0 will give me 0. So our general equation will be n equal to 135 to infinity. Cn is replaced by 4 EDC by n pi sin n omega t, because phi n is 0. Now what is my RMS value of the nth harmonic? That will be 4 EDC by n pi, because this is a maximum value. This is Bm sin omega t, and you know the RMS value of a sine wave is maximum value by root 2. So maximum value divided by root 2. If you recall yesterday's slide or go through the slide after this lecture, you would have seen E naught n RMS for your half bridge inverter was root 2 EDC by n pi. Now it is 2 root 2 EDC by n pi. So all values which will get in half bridge will be multiplied. Simply close your eyes and multiply it by 2. No need to think about anything. So E naught 1 RMS, so n replaced by 1. E naught 3 RMS, n replaced by 3. So accordingly you can find out. Switch voltage and current ratings. V naught CEO is EDC over here. IT average EDC by 2R, IT RMS EDC by root 2R, IT peak EDC by R. These are all the values. So next we'll go into the problem of the regarding your full bridge converter. Yesterday's problem only I have taken, only I have changed the inverter to be full bridge and calculated the same things over here. Now yesterday we had a center tap DC voltage, right? Because in half bridge inverter, recall the DC voltage was EDC by 2. So it is a good way of saying that voltage to be center tapped. So if my center tap voltage is 96 by 2, that means that 96 volt, that means it is EDC by 2. But here directly see DC input voltage is given. So it is 48 volts. So EDC will be direct 48 volts. So what is the RMS value of output voltage? We have just now calculated will be equal to EDC. So E naught RMS is equal to EDC is equal to 48. What will be the fundamental component? So fundamental component 2 root 2 EDC by pi, or remember the general one 2 root 2 EDC by n pi. So for fundamental, n will be replaced by 1. See, 2 root 2 EDC by n pi, n replaced by 1, substitute your EDC as 48, get your value as 43.2. And yesterday we had found out how to find the harmonics. You need to calculate your fundamental and divide it by n. So E naught 1 RMS divided by n. So third harmonic will be E naught 1 RMS divided by 3. So 43.22 divided by 3. So always it is necessary to calculate your fundamental component first. Then it will be easy for you to calculate all other harmonics. Similarly goes for 5, 7, 9, 11. 1 divided by 5. E naught 1 divided by 7. This goes divided by 9. This goes divided by 11. And you will calculate the value. As you go on increasing the harmonics, you can see this. As the order of harmonics increases, the effect of it on the output voltage also decreases, because its magnitude goes on decreasing. So what will be the next? What will be the fundamental power consumed by load? Fundamental power means which voltage? Fundamental voltage. And always power is considered in terms of RMS power. So 43.22 square divided by load resistance given as 10. So 43.22 square divided by 10. 186.624. RMS power consumed by load. That means we have to take the RMS voltage, which is 48 volts. So 48 square divided by 10. So 48 square divided by 10. 230. RMS determined by harmonic summation method. Like yesterday what you did? Square root of E naught 1 square plus dot 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 whatever E naught 11 square. So we have added the square of these terms, made the square root 47.18, and it should come close to your actual RMS voltage, which is 48 volts. See, it is coming over here also. You can do these calculations, but procedure is like this. It's very simple calculations over here. But one thing what you should do, you should remember all the formulas. That is very important in power electronics. There are a number of formulas over here. You have to remember the formulas in order to solve the problems and take care of what things are asked. If it is as fundamental component, then n should be 1. If it is as third harmonic power, that means which RMS you should take is your E naught 3, that is 14.4 square by 10. So please take care of what is asked in your question. So up to this, if you have any doubt, you can ask, or we will continue with RL load. Next is our RL load. Okay. So let's continue with our RL load operation. Now in RL load, there will be 4 modes of operation, because the inductor is a charge storing element. So once it will store the charge when the switches are connected, and when the diodes are there in the circuit, it will discharge. So there will be 4 modes of operation. First it will charge through the switches S1 and S2. Then it will discharge through some diodes. Then it will again charge through S3 and S4 and again discharge through the diodes. So if you go to this figure, so if you go to this figure over here, recall yesterday's fact, what we did, how the inductors were discharging. Tell me, if S1 and S2, through S1 and S2 inductor is charging, which diodes will be on while discharging? Anyone? I had told you a simple formula, simple rule to remember. If S1 and S2 are on for this load to charge, which diodes will be on? D1, D3, D2, D4? Anyone?
D4 or D4?
D4 and D3. Correct. Always recall that if the switches are on S1 and S2, or the other diodes will be on. That is S1 and S2. Remember the suffix 1 and 2. So obviously diodes will be on D4 and D3. This is how you remember all these circuits. Okay. So we'll see how this discharges. So S1 and S2 on. This is our first figure. Mode 1 is always same for your RL load and your R load. So this is, we are studying T1 to T. So S1 is on, V01 current flows through this S1, goes through this load in this direction as stated over here, then goes through S2 back to this negative. Now current I01 and our standard direction of current, you know, is entering the load from left to right. So obviously I01 will be positive. If I01 is in this direction, then V01, the left hand terminal will be positive, right hand will be negative. So if you compare with the actual voltage polarity, it will come out to be positive voltage only. So V01 will be positive, that is equal to EDC. Okay. So during T1 to T2, we are getting positive voltage, EDC, and positive current. So you see T1 to T2, we are getting positive voltage, right? Positive voltage over here, and positive current, because it is charging, it is exponentially increasing. Now it is a R load, don't say it will be linear, it has to increase, it has to decrease. You can show linear rise, you can show exponential rise, no problem. But one thing I have told you, if you show linear rise over here, please show over here linear rise or linear fall. Okay, they have shown exponential, don't show like this, please show linear things. Okay, because you are considered over here to be linear. Now S1 and S2 is on, so only during this time IS1 and S2 will be there. See, IS1 and S2 is there only during T1 to T2. All other parameters, ID1, D2 0, IS1, S4 0, ID3, D4 0. Okay, now it has to discharge. When discharging, inductor acts as my source, its polarity changes, maintaining the current direction same. So I02 and I01 direction is same, so I can directly write I02 as positive, since I01 was positive. Now polarity has changed, this is plus, this is minus, because this was minus, this will become plus, this is plus, this will become minus. Now this plus connected to this diode D3, and this minus connected, or if you go to this figure, if you go to it, now load this side has become plus, this side has become minus. So this plus will automatically on this one, and this minus will automatically turn on D4. So obviously this one and this one will be off. So always if it is charging through S1 and S2, it will discharge through D3 and D4. So now D3 and D4 is on, current D3 and D4 is on, current will flow in this direction to the load, to the source. So now voltage polarity has changed, V02 will be negative. See, between T2 and T3, V02 is negative, that is minus EDC. What is my current? Positive only, but discharging, so positive current and discharge. Okay, so this is what happens during this period. Now which diodes are on? D3, D4. So IS1, S2 is 0, ID1, D2 is 0, IS1, S4 is 0. ID3, D4 is nothing but your load current I0. What is my load current? This one. So we have drawn this one over here. So I hope everybody has understood how this graph is coming and how this operation is done. But in your semester exam, what you do, write this one, mode 1, write this one, but write a line over here that the current, when S1 and S2 is connected, the current flows from the positive terminal of EDC through S1 to the load, through S2 and back to minus. And if we compare our I01 direction and V01 polarity with the actual polarity of the circuit, then it will be treated as positive. This sentence you have to write down in exam. Okay, one sentence apart from this. for every mode. Rest all are same. Okay. Now during T3 to T4, which switch will be on? S3 and S4. Now if S3 and S4 is on, current will flow from this positive in this direction. So I03 has changed its direction, so it will be negative. If I03 is entering in this direction, V03, this one will be positive, this will be negative, because now inductor is charging. So V03 will be again negative. So V03 is during which period? T3 to T4. So T3 to T4 is during this period. See, we are getting negative voltage minus it is. Current is also negative but charging, so increasing in the negative direction. So increasing in the negative direction. Now it has to discharge. Obviously, which diodes will be on? D1 and D2. Now if you check your polarities, okay, the polarity should be changed over here, because this will be plus, this will be minus, because inductor has changed its polarity. I'll change this diagram and send it to you. So now polarity has changed, plus and minus. So minus connected to this minus, plus connected to this plus. Automatically this turns on and current flows from this load to the source. Now I04 is having the same direction as I03, so it will be negative, but V04 has changed its polarity, so it has become positive. So you can read this region also, or we can read the region between before T1. This is nothing but T4 to T1. So we are having positive voltage but negative current. And during this, which is on D1 and D2, so obviously during this region up to this, D1 and D2 will be on, so only D1 and D2 current is shown. Okay, this current, but see again diodes, we have to show positive current, so current is shown in the positive direction. All other currents are zero. All other currents are zero. So this is how your RL load operates. Same as your. So these operations are also same as your RL load in half bridge inverter. Only thing is that the supply voltage is EDC over here. Rest all are same. Now over here we generally find out the instantaneous current. If you recall your previous formulas, we had found out 4 EDC by N pi. So substituted over here 4 EDC by N pi divided by the impedance. And current will be lagging because it is an inductive load. So sin n omega t minus theta n. Okay, and you can calculate your fundamental power. I1 RMS you can calculate by substituting over here. This is my magnitude maximum value. So divided by √2, you will get your RMS value. And since we are finding out fundamental power, all the n terms over here will be replaced by 1. So that is what is done over here, and P1 RMS is calculated. These are just normal formulas which you need to calculate. Only thing you should remember this as your I max. So if you divide this by √2, you will get your IRMS. All formulas same. These things we had done similarly of RL load in half bridge inverter. Now we'll take all problems what we discussed were RL load problems. Now we'll take a simple problem with RLC load or RL load, whatever you want to take. Where you can take a problem and do it. Okay. So let's take a RLC load and check what will be my answers over there. Now in RL, whenever we are taking RLC load, our problems calculations will be little bit hectic. Okay, please take care of this. Because we have to find out the impedances again and again, and when you are finding impedances, there is always an n term over here. For third harmonic you have to give 3, for fifth harmonic you have to give 5. Like this, impedances has to be calculated again and again. You just can't do Z1 by 3 and get Z3, because that is not a factor that is included. Because n, see how n is related over here. You can't divide by n and get that value, which we did in RMS, the E1 RMS, E3 RMS calculations. So over here, little bit calculations are linear. So what we have to do, we have to, first what we did, we written our values, EDC, R, L from the question, and inverter frequency is given 400 Hz, so we can easily find out XL and XC. So XL is 2 pi FL, Substituting your values of F 400 Hertz over here, L as 10 millihenry, will get 25.13 ohms. Similarly, if you calculate XC, what you will get? 1 by 2 pi FC. 1 by 2 pi FC, 1 by 2 pi into 400 into 52 into 10 to the power minus 6 is equal to 7.7 ohms. So all the values accordingly we will put it. Now what is Zn? R square plus XL minus XC square, you know, right? But in that XL there is a frequency included, so XL will be multiplied by N. So XC will be divided by N because there is a frequency in the denominator. So XC by N. So XL and XC are already calculated. Now you can substitute in XL and XC, you can substitute and find out the values accordingly. But as a whole, Z3 can't be written as Z1 by 3. But XL, you can do it. 3XL, this is 5XL because this is directly proportional. And over here it is inversely proportional. So you can directly divide it. So take care of how we are using the formulas. So what will be Z1? R will be written directly 10 ohm. So 10 square. N will be replaced by 1. XL, what is XL? 25.13 minus 7.7 ohms a whole square. You will get 20.09. Now what is Z3? This N will be replaced by 3. So see over here 3. 3 into 25.13. What is XC? 7.7 divided by 3 whole square. 7.7 divided by 3 whole square equal to 73.5. Now Z5, you replace all N by 5. See, N by 5. This N over here, N is replaced by 5. Calculate your values. Similarly, you can find out Z7 and Z9. Hopefully, sorry. Hopefully, you have understood the calculations, how it is done. Z1 to Z9, just your direct formulas, R square plus XL minus XC square. How it is dependent upon frequency, it is N times because it is directly proportional. Over here, XC is inversely proportional, so XC by N. Please take care of the formulas which are used over here. Okay. So next what we are doing, we will calculate the RMS value. First question, RMS value of current at fundamental frequency. So we know the RMS value of voltage is 4 EDC by root 2 N pi, we are derived. So N will be replaced by 1. So it will be 4 by root 2 pi. 4 by root 2 pi is nothing but 0.9 EDC. So we are writing the general formula first. 4 by root 2 pi is 0.9 EDC by N. What is EDC? 220 as given in question. So it will be 198 by N. What will be the harmonic component? IN. So EN by Zn. This you know, V by Z will be this one. So IN will be EN by Zn. That is 198 by N divided by Zn. So that gives you 198 divided by N Zn. Now RMS value of output voltage at fundamental frequency. I1. Fundamental value I1. So 198 divided by 1. What is Z1? We had already calculated 20.09. So substituting it over here, okay, it will be 20.09. So 20.09 over here, you will get your values 9.86. Then you can find out similarly your I3, I5, I7, I9. I have not shown the calculation. Hopefully you will find out these values. If you have any doubt, you can stop me and ask me. Only thing what will be difference is 198 divided by N will be replaced by 3 in case of I3. And what will be Zn will be Z3, which is nothing but 73.51. So 198 by 3 into 73.51 will give you 0.897. Similarly, it goes on. Okay, so we are told to find out RMS value of output current. So you can find out square root of I1 square plus I3 square plus I5 square plus dot I9 square. It has not told that you have to use first 5 harmonics. So we had used 4 over here. You can use 5, you can use 7, you can use 9 harmonics, whatever you want to use. The more you increase your number of harmonics, this 9.90 will be closer to your actual RMS voltage by integration method. Now next is your power output. What is your RMS value of current? 9.90. So 9.90 square into R, that will give you 980 watt. And what is your average value of supply current? Supply current, huh? So supply power, what is my supply? What is my, if I consider it to be 100% efficient, so what will be output power? P naught will be is equal to input power. So EDC into I average. So where I average is your in supply current, average current. Okay. So I average will be P naught by EDC. So 980.10 divided by 220 is equal to 4.46. So this is how your calculations are done in RLC load or RL load, but take care of the fact that impedances should be calculated again and again. And generally when we give RLC load, we tell you to find out the current. So it is very important that Z is calculated. So Z formula you have to remember. You already know this formula, only a factor is included N over here. Lastly, today's discussion, we have performance parameters and basis of that problems. Okay, so I am giving this up to you to study all these definitions and what is this. We'll just discuss very briefly and go with the problems, how it is solved. Now, first one, we generally in the output of the inverter, we generally don't have a pure sine wave. So you are seeing that we are getting a square wave. Later we will get a step waveform. So there are many harmonics in your output voltage. So we need to measure those harmonics. How those harmonics are affecting my output voltage. We have to make a calculation of that. So those calculations are dependent on some factors. Harmonic factors, total harmonic distortion, distortion factor means how the waveform is distorted from the actual wave. So those are the calculations. Harmonic factor, total harmonic distortion, distortion factor, and last one is lowest order harmonic. Lowest order harmonic is always the simple third order harmonic, because third order harmonic is the lowest one. So these are the important formulas we should remember. HFN is your harmonic factor at nth harmonic, which is given by En RMS. That is, if it is third harmonic we are calculating, which is E3 RMS divided by E1 RMS. All are calculated with respect to your fundamental component. So THD, because fundamental component always looks alike your output voltage or your sine wave, because fundamental component has a frequency of 50 Hz. Our output is also having a frequency of 50 Hz. So fundamental component looks alike your sine wave only. If you go for third harmonic component, it will have a frequency of 150 Hz. So all comparisons are made with respect to the fundamental component. So THD is square root of E0 square RMS minus E1 square root over of this term by 1, and DF is this formula. We will apply this formula in terms of problem. You will see how to apply these formulas. So I have taken a simple problem over here, a full bridge converter where a R load is there, which is 3 ohms, and a DC input voltage of 48 volt. What we need to determine are the switch ratings, the THD, I have written short forms over here, DF your distortion factor, harmonic factor and distortion factor for the lowest order harmonic, that is obviously your third harmonic. Now switch ratings. I have taken a full bridge inverter which we have just now studied. So switch ratings, VCO is what? EDC. This is EDC by 2R. Average, this is EDC by root 2R. This is EDC by R. We will use direct formulas, no problem with this. So we will use direct formulas. VCO less than equal to 48 volt because EDC is 48. IT average is EDC by 2R, 48 by 2 into 3 because R is taken as 3 over here. IT RMS is EDC by root 2R, so 48 by 3 root 2. And IT peak is equal to EDC by R, that is 48 by 3. is equal to 69. So these are direct calculation. Now we'll go for calculation of THD. So what is our THD formula? E0 RMS square minus E1 square by E1. E1 is E1 RMS only. Clear? E1 RMS. Now, since this is RMS, obviously this one will also be RMS. Now what is E0 RMS? For your full bridge inverter, it is nothing but EDC. So what is EDC? 48 volt. So E0 RMS is 48 volt over here. E1 RMS, we know the formula. En RMS formula is 2 root 2 EDC by n pi. So 1 RMS, E1 RMS will be, n will be replaced by 1. So 2 root 2 EDC by pi. So 2 root 2 into 48 by pi, that gives you 43.21. Now you just substitute in the formula. You already got your 48 volt as E0 RMS. E1 RMS as 43.21. You can calculate your THD. So substitute your formula, root over 48 square minus this square divided by 43.21 will give you 48.37%. Now, distortion factor. We have this formula over here. E1 RMS already calculated 43.21. Now over here, see the formula over here. En RMS by n square. You can take as many number of n over here, but we have taken first 3 harmonics. So 3, 5, 7, first harmonic. So En, how to calculate En? If you recall the fact, you will see that En RMS is nothing but E1 RMS by n. So this En RMS can be replaced by E1 RMS by n. Okay. So 43.2 square, that n comes in the denominator. So n cube this becomes, so 3 cube. So 43.21 square. 43.21 by 3 cube whole square. Okay, this En by n is whole square term. En by n RMS is a whole square term. So En RMS is replaced by E1 RMS by n. So n it comes in the denominator. This becomes n cube. So n cube. Similarly over here, n cube, fifth harmonic 5 cube, and in the numerator is 43.21. Over here also 43.21 divided by 7 cube. You can go on increasing your harmonics order and find out the value. And substitute over here, that gives you your 3.8. And harmonic factor. What is harmonic factor? Given by En RMS by E1 RMS. Since we have told that lowest order harmonics, this will be E3 RMS. So n is replaced by 3. So E3 RMS by E1 RMS. What is E1 RMS? Is nothing but E3 RMS is nothing but E1 RMS by 3. So over here only you can replace E1 RMS by 3. The numerator E1 RMS and denominator E1 RMS cancels out. So it cancels out and becomes 1 by 3. So 33.33%. Please recall, this is also a gate question that comes. What is the harmonic factor of the fifth harmonic component? So it is always 1 by 5. That is 20%. What is the harmonic factor of seventh harmonic component? No need to use any formula. It will be 1 by 7. For the ninth harmonic component, 1 by 9. That is the formula for HF. Okay, so it is directly what order harmonic it is asked, it is 1 by n. And if it is expressed in percentage, so multiplied by 100. And since we are finding DF for this one, so DF is this formula, E1 RMS in the denominator, and DF for which one we are finding? 3. So there will be only one value of n over here, that is 3. That is the first term over here, written over here. So first term only used over here. Since there is a square root, this square will go outside and cancel out with the square root. So ultimately it will be 1 by 3 cube. So 43.21 and this cancels out. So 1 by 27. That is 3.704%. So up to this, we had explained all our performance parameters and our working of our full bridge ESI with R and RL load.